In this video, we're going to talk about Green's theorem. Green's theorem, I consider this to be sort of another shortcut to line integrals. So if we have a region here, so if we have a, sorry about that mark, I'm using a different program. So if we have this region right here, it has to be a two-dimensional region for Green's theorem. We'll have an equivalent of this in 3 dimensions coming up. But for 2 dimensions, if we have a two-dimensional shape, so that's D, it's two-dimensional, it has to be completely closed, so a curve has to be closed by some curve. If that curve is counterclockwise around the region, then it's considered positive orientation. If it's clockwise, it's considered negative orientation. And if so, you would multiply the line integral by a negative. So with this closed curve, what it says, what Green's theorem says, is there's a relationship between the line integral. Here's another way to write the line integral, p dx plus q dy. This little circle here is new. It means that C is closed. And if it is, we could evaluate instead a double integral over this two-dimensional region. And in order to do that, we'd have to take the partial of q with respect to x and subtract the partial of p with respect to y. Notice this is a little unintuitive. Q is the second component of the vector field, but its partial is with respect to x. And p is the first component, but its partial is with respect to y. So again, this is a little unintuitive on which one of these is first. Again, Green's theorem is sort of a shortcut. Now, if C was closed and the vector field happened to be conservative, then the integral itself is just 0. And if it's conservative, these two quantities are equal, and you get 0 right there under the integral. If it's not conservative, then we'll get a different value for the line integral. Let's do an example. All right, let's evaluate the line integral. The vector field is the field square root of x plus 3y in the x component, and x squared plus square root of y in the y component. And this line integral, the line itself, c, is the curve from y, or the curve y equals sine of x from 0, 0 to pi 0, and then the line from pi 0 to 0, 0. So first of all, let's draw out what this curve is. So we've got y equals sine of x. So sine of x. So sine starts on 0, 0, and it goes in this direction. So there's y equals sine of x, and it keeps going, but right there is pi. So I'm going to draw some arrows because it starts at 0, 0, and then it goes to pi. And then it's a line from pi to 0, 0. So it goes back on that line. Now, if we were to evaluate a line integral, we would have to parameterize two different things and then add them together. We'd have to parameterize this curve sine of x first, find the line integral for it, and then we would have to parameterize that line and find a line integral for that, and then add them together. What Green's theorem does for us is we can now look at this as a 2D shape and put it into a double integral and evaluate it that way. So I'm going to write down what Green's theorem is again. It said that we could calculate a line integral by taking a double integral of the partial of q with respect to x minus the partial of p with respect to y. So now what we need to do is figure out what q is and what p is so we can plug it into this formula, and then we'll figure out what the bounds are for that double integral by looking at the picture of on the xy plane. From the vector field, P is going to be the first component, Q is going to be the second. Those always are in alphabetical order. So to set this integral up, first let's take the partial of Q with respect to x. So partial of Q here with respect to x, so that would be a 2x And then that y is a constant, so that would go to 0. Now we're going to subtract the partial of p with respect to y. X is a constant, that would go to 0. Derivative of 3y, that would be 3. So now we have to look at this two-dimensional picture and figure out the bounds from there. If you look at it, to me it looks like a top function and a bottom function. Well, definitely, we wouldn't want to do a right and a left. So I'm going to do a top and a bottom first. That's going to be dy on the inside integral. Dy on the inside integral, where sine of x is the top function. Sine of x is the top function on that 2D shape. And 0 is the bottom function. And then the outside integral would be x's, and x's looks like those are going to go from 0 to pi. Now we're ready to integrate. So integrate with respect to y. I'm going to leave this guy in there, that's 0 to pi. So integrating with respect to y, that would be 2xy minus 3y. And I'm going to evaluate that from 0 to sine of x. So I get, if I plug in sine of x, I've got 2x sine of x minus 3 sine of x. And then when I plug in 0, those just go to 0. All right, now evaluating this integral, sine of x, that one won't be too bad, but this x sine of x, that is, I'm going to have to use tabular for that guy. So I'm going to choose u as 2x and dv as sine of x. I'll take the derivative of 2x until I hit 0. I'm going to integrate sine of x. So integral of sine would be negative cosine. Integral of negative cosine would be a negative sine. I always like to check my pluses and minuses here. So derivative of sine would be cosine. Cosine would be, okay, I think I have those okay. Multiply diagonally. First one's going to be positive. Second one I'm going to multiply by a negative. So that first integral, I'm going to get a negative 2x cosine of x. And on the second one, I'm going to get a positive 2 sine of x. And then we've got this integral of negative 3 sine. So integral of sine is a negative cosine, so that's going to become a plus 3 cosine of x. And we're going to evaluate all of this from 0 to pi. Alright, so the first one, I'm going to have negative 2 pi, and then cosine of pi is negative 1. Sine of pi is 0. Cosine of pi is negative 1. Then in this next term I've got a 0, so I'm subtracting because it's a lower bound, a negative 0. Sine of 0 is 0. And cosine of 0, I've got to subtract because it's a lower bound. Cosine of 0 is 1, so we would get a minus 3. So combine these all together here, and it looks like we've got a positive 2 pi and a, let's see, a minus 3 and a minus 3, so a minus 6. Now there's a detail that I've left off in all of this, and that's the fact that this shape here is, these arrows are going clockwise. And clockwise means that there's negative notation in all of this. So all of these integrals should really have a negative out in front, a negative out in front of all of that, and negative out in front of all of that, and a negative in front of that. So it means that our final answer should really be negative 2 pi plus 6 because of the negative notation. So we used Green's theorem to evaluate this line integral, and because there were two different curves surrounding a 2D shape, Green's theorem ended up being quite a bit easier than doing two different line integrals and then adding them together.